Wonderful. I will start slowly. I will start where Leo finished, presenting you the picture of smectic A and discussing with you the free energy density. So something is wrong with the projector. It's connected, but control.
Oh, it's saying it's still.
Oh, okay. Yes, okay, good, thank you. I will speak about lamellar phases in general because for many of those the elastic description is exactly the same. The only requirement is that the scale of your deformations is much larger than the period of the structure. So as Leo already explained, if the deformations of layers are relatively small, so that we can describe the impurities effects, or we can describe the dislocations or undulations and things like that, then we are operating with the free energy density written here, which is comprised of the compressibility B term and the curvature K term. And as Leo explained, to make sure that we are not losing the equidistance of layers when we rotate the system as the whole, we add this nonlinear term that makes life of many people rather complicated. So the question is that, again, in this expression, we see two material constants, K and B, and they are of different dimension. And if we take a square root of the ratio of the two, we will find length. And the question is, what is this length? Exactly, this would be something that we would anticipate. And again, until you measure something, you are not quite sure about this. And there is a very simple approach to measure lambda, of course, besides the direct measurements of K and B separately, but that turns out to be not that simple. The simplest approach is to find a defect, such as a dislocation shown here, and make sure that other defects and boundaries are very, very far away from this core of the disconation, and see the vector profile, try to see the layers profile around the dislocation. And there is an expression that predicts how this layers profile should look like when you take the nonlinear version of the elasticity. And you just fit with your data, and you find out that lambda is indeed the quantity that is close to the period, although not quite. It's smaller. And when lambda is smaller than the period, you are even more kind of entitled to use the nonlinear version of the theory, because the linear wouldn't give you the nice fit here. So then there are many situations when you are interested in curvatures that are making the entire turn by 360 degrees. And in that case, it's more convenient to speak about the elasticity of Smectics in a different format, using the ideas about principal radii of the layers. So you are dealing with two elastic terms. One is responsible for the mean curvature of the layers. This is the first term. The second one is the Gaussian curvature of the layers. In kind of two-dimensional problems, it doesn't play any role because one of the r's would be infinitely large. So you have 0 instead of this term. And then I'm using the same expression for the compressibility term, but now instead of using u as the phase variable, I am just using d, the actual thickness of the layer, and its departure from the equilibrium value of the d. Now, consider a situation when you have a large volume of a liquid crystal of a smectic type. Let's say it might be a droplet, again suspended, freely suspended in, let's say, glycerol or water. So the boundary conditions of the anchoring is tangential, as I said. So you are trying to create the filling of this droplet with the smectic layers, and the naive approach would be probably just start growing layers from the boundary inwards. But since the space for these layers is constantly decreasing, you have to introduce a lot of dislocations that would account for interrupted layers. Another approach, which is kind of a little bit more complex geometrically, but in fact it's a simpler one, is that you are trying to do the same problem with the idea of curvatures. So you grow the layers from the surface, and then you bend them around so that they meet the surface again, and then somehow you arrange for the rest of the volume. So if you think about this problem from the point of view of free energy density, what you find out is that when we have the radius of the system much larger than the period or lambda, then it turns out that the expected value of curvature energy and the expected value of the compressibility energy are very much different. If you take the ratio and if you recall that lambda is nothing else but something close to the periodicity of the smectic phase, you would realize that this quantity, if you are using equally compressibility and curvature deformations, is very, very small. It's on the order of lambda over r, which is much smaller than 1 when the size of the system is macroscopic. So you conclude that for large scales, when we have large deformation of layers, the compressibility term can be simply ignored, and you have to first of all think about the curvature deformations of the layers. And this is exactly what leads us to understanding how Georges Friedel found out without X-ray that smectics are what they are. So the reason is purely geometrical. Imagine that you have a curved layer of a smectic. It's curved for whatever reason, boundary conditions or the external field. And since it's a three-dimensional system, you grow the next layer that is parallel to it, and you have to preserve the equidistance of the layers. Because as we just learned, if we are not preserving the equidistance, then this compressibility term becomes very costly energetically. So when you do this, what happens is that the radii of curvature that are characteristic for each and every layer would inscribe some line in 2 dimensions or some surface in 3 dimensions. And when you go closer to this focal surface, the radii of curvature become very small and might become comparable to the thickness of the smectic layer. So you are creating very, very strong deformations of the layers. And the 3-dimensional version of this thing is shown here. So this grayish black layers on top and the bottom are just focal surfaces associated with the family of equidistant flexible smectic layers. Okay, if you think about what should be the energy that you need to spend to create such a wall, then it's something incredibly high, because it's the condensation energy of the smectic, say the energy you need to spend to melt it into the nematic, multiplied by the area of the surface. So it doesn't look like a good solution. And what Mother Nature does, it simply shrinks these surfaces into lines, focal lines. And it turns out that if you want the singularities associated with your family of flexible, one-dimensionally, periodically ordered layers to be degenerate into lines, then these lines might be only of 3 basic types. One most common situation is the pair of lines represent 2 confocal ellipse and hyperbola. So confocal ellipse and hyperbola. Another solution is when the 2 represent 2 confocal parabola. And the third solution, which is kind of the degenerate case of the second one, is a circle and a straight line. So these 3 types of defect pairs give you the packing of flexible equidistant smectic layers that are equidistant everywhere. You might see this is the Mathematica created image, that the layers are really appearing to be perfectly equidistant everywhere, except, of course, for these 2 disconation lines. But again, these are the lines, and their energy scales as the length of the lines, not as an area of the focal surface that was there previously before I try to find the better energetical solution. So geometrically, the idea that there are packings of flexible layers that have focal surfaces being degenerate into the lines was discovered by Dupin. This is why these lines are called not lines, but the surfaces are called by the people the Dupin Cyelides. And it's interesting that Maxwell was aware of this geometrical solution because he wrote an article about the cyclide and said if I have the source of light somewhere that is a piece of line here and the image is a piece of line there, then the waves propagate by the Dupin Cyelides shape. So, and this is true because this construction has an interesting property that all the director lines in this configuration are straight lines. It's like the wave vectors of the beams propagating in the isotropic medium. And the director lines join the points on the hyperbola to all the points on the ellipse and vice versa.
Can you say, what happens with light? What do you see? You see these, how does it manifest itself? Well, just with light, I'm saying just not for Smectic.
For light? Yeah. Caustics and stuff like that. So waves kind of propagate.
Like a sharp.
Right. Yeah. So, but this is how it manifests itself in the case of Smectics. So light is being scattered at these singularities, but you clearly see elliptical bases. Sometimes, if you're happy, if you're lucky, I'm sorry, you see the hyperbola. This is the droplet. This is the droplet that I wanted to kind of show you on the blackboard. So this is precisely how the Smectic adapts to the spherical confinement. It produces the focal conic domains with the bases at the surface, and there the boundary conditions are tangential, and then there are no kind of dislocations. Everything is just curvatures. So I'm not willing to spend too much time on these things because geometrically it might be complex, but just for those of you who might be interested in the theme, I will just flash a couple of slides how you describe these things analytically so that you can, for example, calculate the energy. So you might start with just parameterization of the ellipse and hyperbola in some two other coordinates that are defined on the surface of cyclids. This is the obvious parameterization of points on the let me see, on the ellipse, and this is for the hyperbola. And then you write down the distance between m and m prime, m double prime and m prime, and this distance is from parameterization is something like that. And then since this distance is nothing else but the two radii of curvature, right? Because the radii of curvature start at the focal lines. That's why the focal lines are focal lines. So you have the opportunity to write down the, to introduce the third coordinate, which is r, which simply separates one layer from the other. So what I do here for the distance m double prime m prime, which is nothing else but the sum of two principal radii, taken with a negative sign here because we have to remember about the algebraic sign of this radii there of opposite sign. So I just add and reduce, take away the same r, and then I call this quantity r2 and the second quantity r1. And then I am done. I can write down the free energy density in this curvature form, and I only need to find out the element of volume, which is not a difficult thing. And I can describe the elastic energy of the focal conic domains. And as you might see here, it boils down to a very nice expression when the focal conic domain is of toroidal symmetry. Here we have a very simple expression, and there is no surprise in the fact that the energy scales as elastic constant multiplied by the size of the domain's base, which is a linear quantity. So with this now you can explain analytically things like filling of the droplet. So here what you're dealing with, you start with the concentric system of spheres, and then you kind of facet it with the focal conic domain, that operation saves you the surface anchoring energy because you replace the homeotropic orientation of molecules at the surface with tangential. That saves you the surface energy. Of course, you have to pay the price of distortions different from the spherical one. So that's fine, but you just continue to do that because you know that the surface energy scales as WR squared, and the elastic scales as the KB, where B is now the radius of the circular base of the focal conic domain. So then you continue, for example, in the pattern that was considered many years ago, centuries actually, by Apollonius, and you boil down the system to the balance of the gain in surface energy and the losses in elastic energy, and you find out that this iteration of focal conic domains will persist till some quantity, which is k over delta gamma, or in other notations, k over w, the same anchoring strengths that we considered before.
I missed it. So the circles in the right picture, how do they correspond to
So I just, I make my droplet very big, and I am looking locally at what's happening. So this is the surface of the droplet. It's very big. So now I'm looking at this piece. So there were focal conic domains here and there, but now I'm left with this triangle. So I inscribe the smaller and yet smaller and smaller focal conic domain so that I gain tangential orientation of molecules everywhere.
Where's the
Apex?
cyclide?
They're all Dupin Cyelides. This is, by the way, also Dupin cyclide because it has the focal surface, which is a point.
Is that singularity there?
It's a straight line, yeah.
Straight line, okay.
And this is the ellipse.
The sphere, basically.
Right.
Okay.
So I cut out the conical piece and I plug it in with this focal conic domain. So there are some other interesting geometries. For example, grain boundaries. If you have two pieces of smectic that look into different directions, then depending on the angle of misalignment, you have different situation with the relaxation of the strain. It's something that might be represented as the dislocation wall when the angle is really small, or when the angle is close to, it should be pi, then it's the model of curvature presented by Dejean. But when the angle is really nothing between the two limiting cases, then what happens is prompted by this picture. Turns out that you can pack the focal conic domains next to each other in a very nice fashion so that the layers smoothly go from one focal conic domain to another. And if you see from this side, you can immediately realize that I can add the layers to these two tilted families of the kind of circular cuts of the Dupin Cyelides, and I would have my grain boundary. I will skip the math, it's messy, but the experiments really show the existence of focal conic domains that relax the grain boundary in smectics. So that's all I wanted to say about the focal conic domains and smectics. There are some other things, especially with this. You can find, for example, if you have a smectic on the substrate and the layers want to be parallel to this substrate, then it turns out that a very small distortion, let's say 1 millimeter wide, would create the distortions of layers in the vertical direction that expand over astronomically large distances. In this case, 1 millimeter might cause you something like 100 meters of kind of feeling of the presence of this little thing. So it's an interesting result of elasticity of smectics. Any questions? Okay, then the final lecture is about dynamics of liquid crystals. So, yeah, this is one of the experiments that inspired us to do the research in this area. It's just two plain glass spheres that move in the liquid crystal when there is an AC electric field applied to the liquid crystal. I will explain in details later. So this is the outline. We first start with kind of basics, and I will try to cover it more or less quickly because, again, this is the area that has been developed over the last 40 years, well known. Then I would go to the statics of colloids. I will introduce a little bit the colloids to you, and I will be talking about dynamics of colloids in liquid crystal. So as I told you, liquid crystals have an isotropy of each and every material property. You measure the refractive index, it's anisotropic. You measure dielectric permittivity, it's anisotropic. Viscosities are also anisotropic. And the first person to show it was Mieszowicz, who was working, I think, in Krakow at the time and published 2 articles in Nature that measured the viscosity of the liquid crystal when there is a strong magnetic field that fixes the orientation of the overall director. So he fixes the orientation of the director with respect to the shear direction, and in one case when the director is looking towards you, so it's tilted, the x-axis is looking actually towards you, he would get 1 value of the viscosity. If it's horizontal, it's another value of the viscosity, and when it's vertical, it's yet the 3rd value of the viscosity. And by the way, his experiments were so nice that when people remeasured them about 10 years ago, they couldn't find a difference more than 2 or 3%. So with this came, of course, a huge interest of theorists to the problem of how do you describe viscous properties of pneumatics. And there were 2 schools of thoughts that kind of produced similar results, and yet these results slightly differ in some, I would say, non-significant details. But the bottom line is that the viscous stress tensor in the pneumatic liquid crystal, this is pneumatic, I'll be talking about pneumatics only for the rest of today. So depend not only on the gradients of velocities, like in this term, and this term represents kind of isotropic viscosity, because you see the tensor Aij is nothing else but the symmetric tensor of velocity gradients. But this sigma depends also on the rotation of the director, expressed here through the values like n, vector n. And there are also terms in which you have both the gradients of velocity and the components of the director. So it turns out that there are, in fact, 5 different viscosities of the pneumatic liquid crystal, but 2 of them are relevant only when the deformations are really strong. When the deformations are not that strong, this can be reduced to 3 Mieszowicz coefficients that have been introduced by Mieszowicz. Now, the director dynamics is shown here. I am not going to kind of derive it from the first principles. You can find textbooks that do this. But it's basically telling you that the dynamics is defined by the balance of torques. The torques that come in the first expression are nothing else but the torques associated with the elasticity and action of the external electric field, body forces, such as electric field that acts on the dielectrically anisotropic liquid crystal. And on the right-hand side, you have kind of a viscous response. Now, if you look at the expression for this little vector h, and the name here, molecular field, and especially at this part and this part, you would realize that this is something very close to what we already met. Well, we were trying to minimize the elastic energy for hybrid aligned pneumatic film and for Frederiks effect. And in fact, when we were looking at, say, the Frederiks effect, what we had, the early Lagrange equation that looked something like this. Turns out that if you calculate the torques here on the left-hand side, you would obtain exactly the same expression. The only difference here, I just put electric field instead of magnetic field because I would tell you how quickly the liquid crystal display can switch in the electric field. And the only difference is that instead of 0 in the viscous dynamic problem, I put the viscous response that comes from this second term. So this general director equation tells you that the torques associated with elasticity and external field are balanced by the torques of viscous relaxation. And if you need to solve the dynamics, you just compare the two of them. If you are not interested in the dynamics, you say, this is 0. I'm just interested to have n parallel to the molecular field. And that means exactly that you're dealing with the Euler-Lagrange equation in this form, where on the right-hand side, you have a 0. So in this particular case, it's not difficult to write down this, and it was already written. So it's the same equation of Euler-Lagrange. Only on the right-hand side, I have the viscous relaxation. This gamma 1 is nothing else but the combination of two alphas that I introduced to you as 5 different viscous coefficients.
Sorry, in the previous slide,
Yep.
little n cross big N. Big N has time derivative.
Yes, n has.
That's not. Is that part of your viscous term that you're?
Right, but it's not. It's just not the n that rotates by itself. It's when n rotates differently from the body of the nematic, then you have this term non-zero.
So that's a separate term than what you have gamma theta dot on the next one. Like,
no. In fact, it's the same thing.
Same one.
Yeah, it's the same. Yeah, it's the same thing. So, but in our simplified, so what are the simplifications here? It's kind of one-dimensional problem. Theta depends only on one coordinate. And theta is assumed to be small. Then we can write this left-hand side and right-hand side. The physics will be preserved. For example, you can ask yourself, so how long would it take for me to realign the director along the electric field? And the answer would obviously depend on how big is your electric field. If you apply a very strong electric field, this term is much higher than this term. This can be neglected, and you have a very simple equation that any experimentalist can solve. It will be an exponential thing with characteristic time defined by the ratio of the gamma and electric field squared with an obvious coefficient that depends on delta epsilon. So with typical values, you're getting, well, not typical, but this is kind of on the higher end. You're getting 0.2 micrometers. Now, if you remove the field, then there is a relaxation time when the director goes back to the planar state, and that is defined by this term now and this term. And even from dimensional analysis, except for this pi square, you could find out that the quantity is proportional to the thickness of the cell squared. And this is the problem, because it cannot, in practical devices, thickness of the cell cannot be very small. Otherwise, we wouldn't have enough of optical contrast. So it's like 5 micrometers in the typical display, divided by the elastic constant. So if you put the numbers there, you would find that this is 1 to 10 milliseconds. It's right on the edge of what is acceptable. So when people are trying to work to kind of make better materials with lower viscosity and higher elastic constants and things like that to make this quantity going down. But there are also some different approaches. Instead of realigning the director, you might work in the configuration when the director doesn't want to realign. For example, here you have a director in the planar cell, and delta epsilon is negative. That means if I am applying the electric field across the cell, the director does not need to realign because it's already in the energetically preferred direction. But what happens is that, remember, director is not the whole story about the order in the nematic liquid crystal. There is also the degree of order around this direction. And when you apply electric field, you kind of force the molecules to be more parallel to the director. And that creates optical response. And as you might see here, the optical response is very fast. This scale is in nanoseconds, so it takes like 10 nanoseconds to create rather substantial optical response. So the anisotropy of viscosity and the presence of long-range orientational order lead to decoupling between the two. As you already seen from the expression for sigma, there are terms in which you have components of the director and the gradients of the velocity, and So what happens is that the result of this is that if you have the flow in the system, that flow might realign the director. And the opposite is true. If you have realignment of the director, that creates the flow. The second problem is a big problem for display industry, but I would like just to illustrate the statement with this simple experiment. So this is a thermal expansion of the liquid crystal in the capillary. So you just fill the capillary with the liquid crystal, and then you either cool it down or heat it up so that the material needs to expand, and because of that, the material flows. And I don't know why this movie doesn't work. No, maybe it does work. And so what happens is that originally the director looks at you, and you remember this black screen. That was the texture that you would have, right? But once you start heating, you see that there is a bright sequence of interference colors, and it goes as long as you keep heating the sample. And then you stop heating, and the system relaxes back to the black state. Actually, it was cooling. Now you would start heating. But the same thing happened. Without looking at the bottom, you wouldn't tell whether it was heating or cooling. So it's kind of totally reversible. So how do we understand this effect? Very simple. First, we need to establish the velocity caused by the change in the density. And this is one of those rare cases when you cannot call your fluid incompressible, because when you have thermal expansion, the density changes, and we assume that it is changing linearly with time. This is rho naught at some temperature. This is expansion coefficient. This is the rate with which you change the temperature. So you use the continuity equation where this is non-zero. And you kind of already from here see that there should be a velocity of flow that is growing linearly with the distance from the center of the capillary x. And then since you can take the Stokes equation to find the concrete expression for the velocity profile, you find it here, and it's like a Puazeil flow. There is kind of no difference from the isotropic fluid, except that now you have the director that wants to be vertical, but this flow wants to realign the director. And to find out the tilt angle, you just consider the restoring torque of elasticity, K3, and the second gradient of the angle with respect to the vertical coordinate, and the aligning force of the velocity gradient. And if you plug this into this, you would find the equation for theta that looks like that. So this is the profile of the director that is caused by the thermal expansion. So it's interesting result, because if you thermally expand, for example, water, nothing interesting happens most of the time. If you thermally expand solid, it's the same lattice before and after, just bigger period. But in the liquid crystal, you have this non-trivial transformation in the director field that just, again, illustrates that flow and the gradients of velocities can realign the director. Okay, with this, so this is just a brief introduction into the viscous phenomena in pneumatic liquid crystals that are anisotropic. Now we make the system a little bit more complicated by adding colloidal particles. It's like in Eric's talk today, it was some medium in which we add, let's say, droplets of glycerol or something else. In our case, most of the time it will be solid particles. So how many of you can give the definition of a colloid? Wonderful. Give us the definition of the colloid.
Particles in micron size.
Micron size. What's special about the micron size?
Because of Brownian motion, they flow around.
Exactly. So if I would have a container, thank you, with let's say water and some particles embedded, typically the density of water and particles that are solid are different, and because of that, gravity would pull the stuff down, and it will sediment, as people say, at the bottom of this container. But now if the particle is small, then the Brownian motion starts to enter the scene, and it at the about 1 micrometer scale and smaller, what happens is that the thermal fluctuations are strong enough to kind of keep the particles bouncing away from the bottom. And this limiting scale, about 1 micrometer, is called the scale of colloidal science, and everything that is kind of smaller is called a colloid. So this is one interesting thing, so that colloids do not sediment that easily. And an example is the simplest example that many of you drink during the breakfast is what? Milk, exactly. So this is sedimentation. Another interesting property that people explore in colloids is the fact that when you apply electric field to a colloidal dispersion, you might observe some motion. You use it to separate DNA. You use it in devices such as Kindle. Who has Kindle? Yeah, wonderful. Wow, so many people. Throw it away, buy a electric crystal display. No, it's a wonderful device, but its principle is electrophoresis. You have particles that are driven by the DC electric field, and this is what creates the contrast. So we were just interested to see what would happen if instead of the isotropic solution or solvent, you place the colloids in the nematic liquid crystal. So, and then if you also would apply electric field to see whether there is an interesting variation of this electrophoretic motion. So let me just refresh in your memory the important thing about the balance of not the viscosity, but elasticity and the surface anchoring. So it's a similar problem to the problem of the droplet of a nematic dispersed in, let's say, water, but now it's kind of inversed. I have a particle that is placed in the liquid crystal, and suppose that this particle wants the director to be perpendicular to the surface. So it distorts the director around it. So the scaling is such that the anchoring energy being integrated over the surface of the particle is typically scaling as WR squared. Now, the elastic distortions around this particle scale with the radius of the system. And then if you refresh your middle school algebra, you would realize that for scales that are larger than K over W, and as Lisa told us, it's 1 micrometer in most cases, the surface energy is much more important than the bulk. And below that, the opposite is true. So if I imagine what would happen with the particle, the answer depends on the size of this particle. If the particle is smaller than K over W, then nothing would happen with the director. The director wouldn't notice the presence of this particle. Now, if I have a particle that is larger, then the surface anchoring would tell the director to obey, and the director would obey, and will try to be perpendicular to the surface. This is a naive solution that kind of comes from the original setting. But in fact, if you think about it, instead of this equatorial disclination line, it might be better to shrink it into a point, smaller energy, smaller lengths, and this is exactly what happens as predicted by Lubansky and Stark and observed by Poulin and Weitz some years ago. These deformations lead to an isotropy of colloidal interactions, which is an interesting theme in its own, but I'm not going to talk about this. I would like just to say that, so it's not just some lunacy. You can take a microscope and you can really see the topological defects that are sitting next to the sphere. If the sphere is anchored in the perpendicular way, by the way, Uroš, this is the chromonic material with perpendicular anchoring. You asked the question, so it's possible. So, and this is the sphere also in chromonic with tangential anchoring. You see slightly different deformations. And then if you're interested to see whether it's kind of the same from the side, for example, in this case, it should be axially symmetric, and also in this case, you take the three-dimensional microscope, and you see that, yes, it's kind of, the defect is also seen in the vertical cross-section, but there is something else here, and what is that? There is some unexpected feature in this picture. Look at this scale, 5 micrometers. So this is the piece of glass placed, which has the density of around 2, 10 to the minus 3 in System International, placed in the liquid crystal that has a density that is about 2 times smaller. So the point is that this sphere does not drop to the bottom. It levitates in the bulk. And if I would melt this liquid crystal, I would see that the sphere drops to the bottom of the container. So the sphere levitates in the liquid crystal bulk. Who can tell me why that happens? Exactly. So of course we have gravity as usual, but then, if I'm going to listen to the gravity and pull the particle, closer to the surface, the director gradients will increase, and that is not good. So I have elastic repulsion of the sphere from the bottom. And what is interesting, if you kind of make the back of the envelope calculations, you would find that there is an equilibrium distance of levitation, this z, and it is proportional to the radius of the particle to the power of 1/4 divided by the density difference. It's totally different from the case of isotropic fluids, where the bigger the particle, the harder for it to be a colloid. In pneumatic, everyone, even an elephant, can call itself a colloid, because it will be just hanging up there. And this is an example. This is the same material, but this particle is bigger than this particle, and it levitates better. So let's now consider the Brownian motion of particles in the liquid crystal. So it was shown by Laudet and Poulin and Hanous that when you have a colloidal particle in the pneumatic environment, then it experiences Brownian motion, of course, but this Brownian motion is anisotropic. So if you measure displacement in this direction and in this direction, you would find the law that we thankfully call the Einstein-Smoluchowski law, but it will be a different diffusion coefficient for the displacement parallel to the director and the displacement perpendicular to the director. So that is good, and that is kind of understandable, because we have anisotropy. The parallel displacement is parallel to the director, and the kind of viscosity is smaller than in the perpendicular direction when the motion has to meet the liquid crystal molecules from the side. So, but then, there is this characteristic time that we already met in the Frederiks transition that depends on the typical size. And we have some typical size. So the question is, I have this characteristic time of director relaxation. Would that somehow influence the results or not? So I'm about to talk about this region at small time scales where something might happen just because the director relaxes over those scales. So to have the experiment done properly, we got rid of the birefringence of the liquid crystal. Turned out that Merck, the company in Germany that produces zillions of liquid crystals, some time ago, 25 years ago, developed a material in which delta n is 0. And so we were the first customers who were interested in this liquid crystal. So we bought it because it helps us to eliminate all this, fake imaging effects associated with birefringence. So when we look at the sphere, you probably even notice that I don't even see the hedgehog there, just because the delta n is 0. There is no birefringence. So, and then we measured how the mean square displacement behaves with time. For long time scales, it's a normal behavior. For isotropic fluid, isotropic melt of the same material, it's classic all the way through. But if we have a pneumatic, then for x and for y displacement, we have classic behavior at the beginning, but then something strange happens, and it's better to present it in terms of the velocity autocorrelation function, which basically tells you if I have a particle moving in this direction, what would be the probability of the particle to continue to move in the same direction as opposed to changing the velocity into the opposite direction. So if I plot this quantity for the isotropic fluid, then I get 0. That means that, if the particle was moving this way, then the next step is not correlated. It can go backward or continue to move forward. But in the pneumatic, something interesting happens. At long time scales, it's the same thing. It's 0. But as you decrease the time steps, it goes into what people call subdiffusive regime, and then it goes into superdiffusive regime for both y displacement and x displacements. So how do we understand this? It's just because the liquid crystal influences the Brownian motion of the particle through director relaxation. Suppose that the particle fluctuatively moves to the right-hand side. that causes director distortions that are higher on the right-hand side as opposed to the left-hand side. But since the director is distorted, it pushes this particle back, and you have the subdiffusive regime. But there is also a possibility for the superdiffusion. It's when I have a particle here, and the director fluctuates nearby. Then the particle might be either attracted or repelled from this fluctuative deformation, and that might create the kind of ballistic-like motion, which we call superdiffusion. Okay, and now electrophoresis. So Lake crystals are good in the sense that you can always check the background information. Namely, you can raise the temperature by a few degrees, melt your Lake crystal into the isotropic fluid, and see how things are in the isotropic fluid. And so this is what we did at the beginning of our electrophoresis experiment. We took Lake crystal and melted it, and then put the glass sphere and looked how the velocity of this sphere depends on the applied electric field. And so as you might see, if the field is one direction, then the velocity is in this direction. If we change the polarity, it's in the opposite direction. But the dependency is linear. Very good. It's just the Helmholtz-Smoluchowski expression for classic electrophoresis, and it should be this way. Now we cool the isotropic melt down, and we create these director lines, orientational order in the system. And the particles are such that they create perpendicular alignment. And that means that you have this topological defect, hyperbolic hedgehog, either on the left-hand side or right-hand side. It's just a random thing. But once you create it on one side, it stays there. It cannot go around because there is a huge elastic energy barrier. And so we are also dealing in the geometry when you see the director is already parallel to the electric field everywhere. And so we are not that worried about dielectric Frederiks like relaxation or reorientation of the director. Moreover, in most of the experiments, we are using Lake crystals that are specially designed with delta epsilon being 0. So there is no dielectric torque on the material. So, and then we repeat the same observation. For this blue particle in which the hedgehog is on the left-hand side, we observe that at the beginning, the behavior is kind of linear, but then it is totally strange. I apply the field in one direction, the particle starts to move faster, but then it slows down and even changes the direction. So that's very strange. For that particle, it's the mirror symmetry result. You apply the electric field, and then at some point, the particle changes the directionality of motion. So you don't understand this, but you know the math. You know how to describe this behavior. It's the combination of a linear term and some quadratic term. You have no clue at this moment why you have this quadratic term. But you already can file for the patent that you can drive the particles in the liquid crystal by an AC electric field with 0 mean time average. Because if you take this dependency and now instead of the DC field, you use an AC field, the linear term disappears. The particle just would go back and forth, but there would be no displacement in the long run. But the quadratic term would give you a propulsion in the same direction, no matter what is the polarity of the field, up or down. And this is precisely what you see here. Okay, so you don't understand the mechanism, as I said, so you are trying to think what might be the mechanism. And maybe the simplest way to arrive at understanding is to first consider the electrophoresis and its mechanisms in normal isotropic fluids. So this is the classic linear effect that was described by Helmholtz and Smoluchowski. So they consider the sphere that has surface charges that are kind of dissociating. You have equal number of positive and negative charges, but the positive in this case go into the environment of the electrolyte, and they are trying to go away because of the entropy, but then there is a colonic interaction and attraction to the surface. Some of them come back, and they form what we call double electric layers. Now, despite the fact that the system is electroneutral, if you apply the electric field, what happens is that this electric field kind of rotates this imaginary dipole at the surface of the particle. So the piece of electric double layer is like dipole that the external electric field realigns. And that creates the flow of electrolyte around the particle. And if the particle is free to move, but the tank with the fluid is kind of fixed, then it will be the particle that would move in the applied electric field. And the velocity will be proportional to the electric field. This is the quantity that characterizes the electric double layer around the particle. So, as I said, it's a very kind of general phenomenon that is used in displays, that is used in separation of macromolecules with some variations. But there are some problems, and this is why people are motivated to look for nonlinear electrophoretic phenomena. One of them is that obviously, because of this linear dependency, only DC field can be used to drive the particles. But if I apply a DC, if I wait for a long time, my electrodes are blocked by the ions and there is no electric field. I have to somehow rectify the system again. And that means that it's very difficult to create sustainable flow of the material. Obviously, only charged particles can be moved. If my particle, for whatever reason, is not charged, it wouldn't move. And again, obviously, because of this linear dependency, you can have a motion on the parallel or anti-parallel to the field. For example, you wouldn't be able to create vortices that you might need to mix things at the microscale, in microfluidics, for example.
Are you saying you're separating the positive charges from the negative? They're flowing
Yeah.
in the direction?
Yeah, this is the, if it were not for the separation of charges in the electric double layer, then I wouldn't have electrophoresis. If the charges are sitting next to each other, the external electric field does not create anything to
But even if they're not separated, I mean, even if they're separated, but they separate by a fixed bond, the separation, you still have a neutral object.
It's a neutral object, right?
Because in the uniform electric field, it wouldn't move. Suppose you just have a dipole, it doesn't move in the uniform electric field.
Yeah, but this is creating a torque that rolls around, and then the new ions come, and that creates the average, the flow of the fluid around the particle. The fact that the positive and negative are located in different media, in this case negative, are fixed at the surface of the particle, and the positives are kind of free to move around and to replenish the electric double layer, leads to this phenomenon.
So what is it, can you just say, what is electrophoresis?
It's a motion of the colloidal particle in the externally applied uniform electric field. It's a very subtle effect, and in fact,
and it has a separate name because it's neutral particle.
it's a neutral particle. Of course, if you remember Millikan experiments, right, that told us the elementary charge. So in those cases, the point was to have oil droplets charged. And then you have them flowing in air in the electric field, and that is a different science. Here, the charges are, the system is electroneutral, and it still moves with the linear velocity. So as I said, people are looking for nonlinear things, and this is a somewhat different situation, which is the metallic sphere, highly polarizable sphere. Typically, these spheres do not have much of the surface charge, and but they still might be placed in the electrolyte. And when you apply electric field, what happens is that this sphere is polarized. The conductancy electrons would go to the left and to the right, and they would attract the ions from the electrolyte that would form two clouds. Now, this is the electric field that creates the cloud, so the density of the separated charges should be proportional to the acting electric field. But then if you have the charges separated, there is a Coulomb force that would drive these charges around, and this Coulomb force is nothing else but the product of the charge and the electric field. And since the charge was created by the electric field, you would expect that the dependency is quadratic. And then it was Squires and Bazant who made the next step and said, let's suppose that your sphere is not just a sphere, but it's a Janus sphere. For example, it has one surface that is highly polarizable, a metal, and another one is dielectric. Then I would create the same clouds, but now there is asymmetry in the created flows. And yesterday we had a nice poster from Granik's group that demonstrated experimentally how exactly these genus particles are moving in the AC electric field. And so the physics here is the same as on the left-hand side. The applied electric field causes these clouds of ions around the particle, the polarizable part of the particle being separated, and then acts on these clouds and causes the motion. And this motion has the velocity that is proportional to the square of the electric field. Vele was the first to observe it experimentally. So we kind of conclude that in isotropic electrolytes, what we need is to separate the charges. Somehow we need to separate the charges either through the electric double layers, which is kind of independent of the applied electric field, or we can separate them through the polarizable surfaces that kind of collect positive and negative charges around themselves, and then the applied electric field acts on the very same charges it created to move the fluid around. So in liquid crystal, used as an electrolyte, the mechanism of charge separation is different. But we need some mechanism of charge separation to have the motion of the fluid. So this mechanism is rooted in the anisotropy of electric conductivity and in director distortions of the liquid crystal. Let's have a break for a couple of minutes and continue after the break. Okay, let's continue. So the mechanism in Lie crystals is totally different. It depends not so much on the properties of the particle, but it depends mostly exclusively on the properties of the fluid. And it's dramatically different situation because if in the isotropic electrolyte I need to kind of satisfy certain conditions on the properties of the particle, on the properties of the cargo that I want to move, in the Lie crystal case, all these requirements are released, and my particle might be practically anything, piece of glass, a piece of metal, it can be fluid, water, droplet, or almost whatever. So the roots of this mechanism are in the phenomenon that is known for many years now and is called Carr-Helfrich effect. So in 60s, it was noticed that in some cases, when you have a Lie crystal with a negative dielectric anisotropy, you put it in the cell, and then you apply a vertical electric field, you would think that nothing would happen, right? Because in the case when delta epsilon is negative, the preferred orientation of the director is perpendicular to the field. But people did observe realignment, and it was very puzzling for a few years. But then first Carr, and then Helfrich, Wolfgang Helfrich, who is well known for the theory of membranes and many other things, came up with the solution. They said, look, if we have some ions in the system, and if there is a fluctuation in the director orientation, so that the director, just by fluctuation, turns this way, then what happens is that because the electric conductivity of ions is anisotropic, that means that the ions prefer to move parallel to the director rather than perpendicular to the director. Then what happens is that in this geometry of the vertically applied electric field, positive ions move up to the top of this director mountain, and negative would go down. But then it will create an additional electric field in the horizontal direction, and that electric field might be enough to sustain the anomalous orientation of the director in the Lie crystal cell. So that was the explanation of the realignment of the director when the initial state of the director is uniform. So you start with the uniform director, you apply the electric field, you see something strange. You explain it by the fact that ionic conductivity is anisotropic. So what would happen if the Lie crystal is already predistorted, for example, because you have the colloidal particle placed in this? So let's just consider this colloidal particle that, because of surface anchoring, wants the director to be curved. So there are always some traces of ions in the Lie crystal. And it turns out that no matter how clean it is, it's always enough ions to cause all the phenomena I'm talking about. So suppose I have these distortions, and it's just a two-dimensional thing. For simplicity, I have normal boundary conditions. This little angle phi is just the deviation of the director from the horizontal orientation that is imposed by the cell outside of this colloid. Okay, so I applied electric field. When I apply electric field, the ions move positive to the left, negative to the right, according to the direction of this field. But the problem is that the director lines are curved, and these ions are like trains that follow the railroad produced by the director. So with this geometry, the negative charges would move to the left and will stop here, and the positive charges would move to the right and condensed here, so that I would create two clouds of separated charges. The electric field is still there, so it acts on these clouds of charges and moves them, but since I have the solid surface here, it moves kind of forward and upwards, and most probably I would create some vortex. So okay, fine. Then let's consider what would happen if I reverse the polarity of the electric field. So the ions again would move, and now because of the different polarity of the electric field, I would have positive cloud on the right-hand side and negative on the left-hand side. But the force that acts on the clouds is the product of the charge and the electric field, and since both of them changed their sign, the product is of the same value. That means that despite the reversal in the polarity of the electric field, the flows would be still the same. Let me show you the previous slide and the next slide. Yeah, so you see this lines go to the top and to the north pole and south pole, and if I change the polarity of the electric field, it's still north pole and south pole. So, but if I change the director configuration, for example, I say, okay, let my particle produce tangential boundary conditions. So the only difference is that now the derivatives of this angle would be of opposite signs. Now I kind of diverge in the director when I approach the left-hand side. You might see that for the same polarity of the electric field, the polarity of charges is opposite, just because of the sign of the director derivatives. So I would expect that my particle would produce flows that go from the north pole to the equatorial plane and from the south pole to the equatorial plane. Okay, it's all just qualitative consideration. Let's do the experiment. Here you have the particle that produces normal boundary conditions, and here is the particle that produces tangential boundary conditions. Here you simply have a surfactant. And as you might see, it is indeed what was expected. Here I kind of take the fluid from the equatorial plane and eject it towards the north and south pole. Here I just do the opposite. The fluid comes from the poles and is being expelled into the horizontal direction. Okay, fine. Then I'm thinking what would happen if my particle has this point defect on the side. Then the symmetry with respect to the vertical plane is broken, and I should observe a pumping effect. And this is indeed what we observe. If the particle is fixed, and if the electric field is acting, then instead of the four kind of identical vortices, I see only two vortices that are relatively small and two bigger vortices that pump the fluid from right to left. This is, by the way, the microparticle velocimetry mapping that shows you the distribution of the velocities. But then you can integrate the data and obtain the pumping efficiency, how much fluid is being pumped per unit time, per unit second from right to left. And you might see here that this is some thousands of micrometers per second being pumped rather efficiently. And in the vertical direction, of course, there is a symmetry with respect to the horizontal plane. There is no pumping. This is an anti-symmetric behavior, so that the fluid is not being pumped. Now, this is the particle that is glued to the substrate. If we release the particle and let it go, then we would see exactly what was shown on the first slide. These free particles will move, but the liquid crystal would just sit there and pretend that it doesn't know nothing. It just does nothing. So that's very good. And now, instead of just calculating the charges going here and there, we can again start with the Maxwell equations and write down now the currents. The currents are present because we are dealing with the electric conductivity. Recall that the currents depend on the tensor of electric conductivity and the applied electric field. And if you have non-zero phi, if the director is non-uniform, then you can see that it's not only the current along the horizontal direction, it's also the current along the vertical direction that the electric field along the x-axis causes. So I apply electric field in this direction, and there is, of course, current in this direction, but there is also a perpendicular current that creates ultimately the separation of charges. And from this simple system of equation, I write down the expression for the density, volume density of electric charges as something that is proportional to an isotropy of conductivity, the gradient of the director field, and the amplitude of the applied I'm sorry, the gradient of the director field and the amplitude of the electric field. Now, if I kind of approximate the gradients of the director field with the inverse radius of the particle, which is a natural thing, more or less, because these director distortions are created by the particle of certain size. And if I equate the Coulomb force, which is a product of this field-induced charge and the electric field itself, if I equate this to the viscous resistance force, density of it, I would get this prediction for the velocity of the fluid around the particle or of the particle with respect to the fluid if the particle is free. So it goes as thing proportional to delta sigma and the radius of the particle and the square of the electric field, which is very important because as we saw, the particles are being driven by the AC electric field. So you can do the experiment by measuring how things depend on the size of the particle. It goes linearly as predicted, and you also can see that the effect of this liquid crystal electrokinetics is rather efficient, because if you compare the velocities in this effect to the velocity of linear electrophoresis in the isotropic fluid, you would see that despite the fact that the viscosity of the liquid crystals is typically somewhat higher than the viscosity of the fluid, of the isotropic fluid, the fact that you separate the charges by huge distances, by the distances that are on the order of the particle size, and this is few, even tens of micrometers, and in the electric double layers you have separation of charges by only few nanometers. This ratio is huge. It shows you that you have an efficient way of moving things around. Okay, so about the colloids, it's that we can replace the isotropic electrolyte with a liquid crystal electrolyte, and that would allow us, when the liquid crystal is deformed, to separate charges around the colloidal particles and move these colloidal particles. And then we can play with the different patterns of the director and make some improvements to kind of design the three-dimensional trajectory of the colloidal particle and do some other things. But I would like now to switch to the last topic of this presentation, which is kind of similar to what you will be exposed to during the next week. It's an example of active matter. So you probably know that there are many ways of inject energy into the condensed matter and to observe some unusual effects. One of the first by Ramaswamy was just the plate filled with solid rod-like particles that were shaken, and you might see here that they create an emetic-like order with disclinations, and these disclinations move around. Then Dogic and his colleagues created a very nice system with micromotors and observed topological turbulence caused by the motion of matter and appearance and annihilation of +1/2 and -1/2 disclinations. You can read this review article recently appeared in Reviews of Modern Physics. So there is an explosive growth of interest to this area, and there are many things that are not known. So we decided that we also would like to explore the active matter, but for us it was important kind of to have a handle on two independent things. One is sometimes they are not independent, sometimes they are dependent, and pretty much so. This is why we wanted to separate them. So we wanted to separate the orientational order in the system from the level of activity. So in the previous examples, like in this case of shaken rods, if I stop shaking, there will be most probably no orientational order. Here, if the cells or motors are dead, there will be probably also no pneumatic order. Yes. Because the density is often not
because the density is
right.
But if the density was high.
No, if the density, of course, yeah. Then, but you know, the collective behavior, for example, in the isotropic dispersion of living bacteria occurs before they reach that.
They get stuck.
Right.
Kind of flow because it's too
Right. So whatever is the thing, but we wanted just to separate the two. So namely, we wanted to have a separate handle on the orientational order, and we wanted to have a separate handle on the activity. And for doing that, we decided that we will be using the lyotropic harmonic liquid crystal that I was talking about, and living bacteria, Bacillus subtilis, that can survive in the environment of this liquid crystal. These chromonics are very friendly to everything of biological origin, and in this way we can kind of control independently the two things. As I said, this work was done from the beginning to the end in collaboration with Igor Aronson at Argonne. So the first experiment is very simple. You just put some quantity of bacteria, not that much, in the lyotropic liquid crystal, and you observe that this thing moves parallel to the director. Very nice. Similar observations were done by other people, and it's kind of natural because there is a viscosity difference and there is elastic interaction between the rod-like bacterium and the surrounding director, so it's expected. The next step, not much different but still different, is you create the distortions of the director field, and these are nothing else but the tactoids of isotropic phase that we explored in detail in the previous lectures. So the director is distorted around this thing, and as you might see, the bacterium follows the trajectory, and so it gives you the idea that you can design the director pathway and the bacterium would just follow this director field. Then there is an interesting thing that if you put some obstacles in front of the bacteria in the liquid crystal, like there was a little thing, this one, located right here. So just watch this thing. Bacterium comes and moves this guy away. So again, here it's a looped movie. A piece of junk, bacterium comes and pushes it to the right-hand side. So, and it does it, yes, a question?
Yeah, but like the particle was moving even before touch.
Yeah, exactly. Yeah, why do you think it's happening?
Yeah, like it's like a plug flow that the bacteria pushes through it, pushes the particle.
Exactly. So the bacterium squirts the jets of water in front of itself, and in wake of itself, it pulls the water from the sides. It's the pusher type of the motion, exactly similar to what we already saw with the colloidal particles in electrophoresis in liquid crystals. But yeah, this is a kind of distance control. There is not a physical contact, but the contact through the ejected fluid coming from the bacterium. So, but the point here, yes? I would guess it's comparable. Schwang is the guy who did all these experiments, so he would know all the details down to nanograms, I would say. So the thing is that if it were a fluid environment, you wouldn't see this effect. Why? Because if there is an obstacle, the bacterium comes, it either pushes the obstacle to the side or it goes around and just continues without doing any useful job. But the nematic forces it to be useful because the bacterium cannot escape this thing because there is a director around. So the bacterium cannot move perpendicularly in this experiment to the director, so it just pushes the obstacle until some fluctuation occurs and bacterium escapes. So the liquid crystal environment allows you to kind of have some glimpse of what's going on with the bacterium itself. Why? Because it's a bifringent medium, and so you can now even see how the flagellum moves, because everything around this flagellum is bifringent. So there is this action of the shear produced by the rotating flagellum onto the bifringent liquid crystal, and you can count these stripes and you can deduce the rotation of the flagellum and the rotation of the head of the bacterium, which are kind of important things if you are studying the swimming behavior of bacterium. If you are close to the phase transition into the isotropic phase of this nematic, then you might have the Wilson camera effect. The moving bacterium shears the liquid crystal to such an extent that it melts, simply because the temperature is close to the melting point, and it leaves this trace of tactoids in its wake. So it's the effects at the individual level of bacteria. An interesting thing would happen when the bacteria have the opportunity to show their collective effects, and that happens when you increase the concentration of them. So as I said, we can independently control activity by simply providing more oxygen or more nitrogen into the chamber. And if you have more oxygen, the bacteria are more active. If more nitrogen, then they are kind of dead. They are never dead. They are always just sleeping. So if they are sleeping, not moving, then they align parallel to the director, which is very nice. And you have a very well-defined nematic, uniformly aligned because you rub the substrate. But then you add a little bit of oxygen, and these bacteria start to move parallel to the director. But since there are many of them, there is some undulation that develops here. And this undulation can be seen in the entire cell. If you supply the oxygen from the left-hand side, you might notice that the period of undulations is decreasing as you have an increased activity, which is kind of proportional to the amount of oxygen available. So I would like to show the movie. This is the change in the system once the oxygen is being supplied. So the mechanism by hand waving arguments is very simple. It's very similar to what Ramaswamy argued for years now. If you have an active particle of the pusher type embedded in the nematic environment, what happens is that if by any fluctuations this particle slightly tilts with respect to the rest of the medium, with respect to the director, then there is a projection of these jets of flow, in our case, onto the horizontal direction, and the nematic becomes unstable with respect to the bulging towards these red arrows to the right or to the left. And of course, since there is an elasticity of the nematic, I cannot make these distortions arbitrarily strong. There is a restoring torque from the elastic response, and by kind of equating in a simple kind of dimensional analysis way the misaligning torque created by the squirting bacterium and the elastic response, I kind of arrive at the estimate for the period of this bending, which would be the square root of elastic constant divided by the activity of the bacterium. And it turns out that if you change the concentrations and if you change the thickness of the cell, you find out that this very simple expression describes the balance of elasticity and activity relatively well. Now, if you increase the activity further, then you have another transition. So the first transition was from a uniform nematic to the nematic with undulations of the band type. If the activity is increased, then these bands kind of exceed the critical radius of curvature, and they start to nucleate pairs of +1/2 and -1/2 disconation, and the system transforms into this totally misaligned structure that is very similar to what Dogic observed, and it's the topological turbulence of point defects. So this is just an introduction to the system. There are many. The activity is associated with the amount of, is controlled by the amount of oxygen. Oh, mathematically, we just, in this misaligning torque, I put some concentration of bacteria and some alpha, which represents my activity. Just. It's not related to the nematic director. It's related to the bacterium. The nematic director comes opposing. The nematic, you see?
A is direct orientation.
Yes.
And C is the concentration.
Right. The elastic energy depends on the derivative of theta with respect to coordinate. No, the torque that is created by the activity depends on the activity and on the angle of the bacterium with respect to the director. My
This term is purely non-equilibrium term. It only occurs in the equation of motion level. It's not part of the
But it does change.
This is a non-equilibrium term. It doesn't
exactly.
It doesn't come from a minimum. Like for example, in the energy, you only can have terms with the gradient power. This term is actually a force that it's not a conservative force. Right?
Basically, that acts on the direct.
Yes, external field. That it's very. First, we even thought that we would be able to describe it as the Frederiks transition or something. Right.
But itself is the dynamic.
Right. So this is kind of our assumption. You know, this is the weakest thing in the entire thing. This is kind of understandable. This, we just assume it's a product of the activity by the angle, and we have a justification that if theta is 0, then there is no realigning torque, exactly like in the Frederiks transition. If the magnetic field is acting perpendicularly to the director, there is no torque. It's only fluctuations that create this torque. Then it increases exponential, and
So it seems to me that that should be representable by distinct fields, kinematic direction, and the local reorientation.
of embedded bacteria.
Yeah, both coupled in each depend on their equation of motion.
Might be, might be. So that's the end of the story. As you understand, we are only at the beginning of all this study. We don't understand many things, including the basic approach to how do we describe these things. But what is clear is that this system is very nice for future studies. Why? Because even from the beginning, you already see how by gently changing the activity, by feeding more oxygen into the system, you change the activity from 0 to some medium value, so that it's just enough to produce undulations of the director. But then you can increase it even further, and these undulations would break into the topological turbulence. And as far as I know, this is the only system in which this scenario is observed experimentally, and so it is clearly of interest to explore it further. So what I was trying to tell you about was that the Licht crystals are fluids with an isotropic viscosity. There are 5 viscous coefficients that makes some of the problems rather difficult to treat. Then there is a coupling between flows and the director. If the flows changes, so does the director. If the director changes, it can cause a flow. The Licht crystal as the electrolytic medium leads to a new mechanism of electrokinetics, in which the charges and the flows are created not because of the properties of the particle that you would want to move, but because of the director distortions in the medium. And in the living Licht crystals case, we have first effects at the individual level. When the bacteria are far away from each other, you can use the Licht crystal to coach the bacteria to do something useful, to bring the cargo to some point or something like that. And if you have collective effects, then you can observe interesting scenario of by which the uniform nematic, that is non-active, is transformed into an active matter with topological turbulence and this intermediate bending instability. So that's it. Thank you very much.